But even though, so today's class we'll be studying what is short circuit ratio. So short circuit ratio is usually available for the alternators and the generators basically. And how it is defined is, it is nothing but it's defined as the ratio of the field current basically required to produce the rated voltage on open circuit to the field current required to circulate rated current at short circuit. Means what? Field current will remain same, so it is the ratio of the what ratio it is the ratio of the open field current required to produce rated voltage. Means rated voltage, when the rated voltage is produced on open circuit, when you are not connecting any load to the end of the circuit, so that means you are opening the circuit. So that time, what is the ratio of the rated voltage, okay, open circuit voltage to the field current required to circulate rated current at short circuit voltage. So when you are short circuit it, at that time you will see the what current is going through it. So I'll be defining and with three phase explain the factors, and we'll explain this has what is short circuit ratio in alternators, and explain and explain the factors. So basically, when we have to define the short circuit ratio, so the solution to this is the question. So how do you define it? So we'll write the short circuit ratio, the short circuit ratio, also in smaller terms SCR, of a synchronous machine. This machine is defined defined as the ratio of field current, or as the ratio of field current required. Means the field current is a constant variable over here, like in the short circuit ratio. So this field current is a variable that is essential here. Field current required, okay, to produce rated voltage, to produce rated voltage rated voltage, okay, at rated voltage on open circuit, open circuit. So this means the rated voltage, you are keeping the field current constant, and what you are doing is that you are removing the load. At that time the voltage would be your open circuit rated voltage, okay, to field current, okay. So you have to keep the field current to field current, okay. Then you short the circuit required to circulate required to circulate rated current on short circuit. So earlier also I have defined you voltage regulation, okay. Can any one of you, Manohar, can you describe me what is voltage regulation? Ratika, what you can tell me what is voltage regulation? Afsa, Afsa, Nalinakshi, can you tell me what is voltage regulation? Huh? Nalinakshi? So if we are describing the voltage regulation, how can we describe the voltage regulation? How do we describe the voltage regulation? Hmm? So basically, what is the voltage regulation? Voltage regulation of a machine. How do you describe? Basically, when voltage regulation of a machine is described as, now I will revise it for you. So it is described as what? Voltage regulation is described as the machine when it is kept on no load, means there is no load connected to it. So when there is no load and machine is opened, so it will be at its rated load. Okay. Then when we connect a load to it, okay, so the difference between the machine at the percentage or the ratio of the machine that is connected at no load minus minus the voltage at full load, okay, by keeping the sending and voltage constant. So you are keeping the sending and voltage constant. Similarly here we are seeing it for the same field current. We are opening the circuit and checking the rated voltage, and for the same field current we are shorting the circuit and seeing the rated the rated current of the machine. So this is called as the short circuit ratio. This is called as short circuit ratio. So similarly, now if we have to define this short circuit ratio, okay, so short circuit ratio can be, if you at least you be in this thing, what I call is um, little bit you have to what I say is uh, vocal in the class, and you have to give you some inputs. So it's a very important factor in case of a machine. So what exactly it does is that it affects the operating characteristics, okay, and basically the physical size and the type of machine, how much it will cost, and the variation of the terminal voltage with change in load, okay, other factors for value of short circuit ratio. So it calculates a lot of factors, and that's exactly the short circuit ratio of a machine. So a short circuit ratio can be affected by your what are the factors that it affects, okay, so that also we have to take into consideration. So what are the factors it is affecting? Factors affecting affected by SCR So number one factor that it affects is that the it affects the voltage regulation. Voltage regulation. So how does it affect the voltage regulation? So if we look carefully, now I defined you the voltage regulation. VR is what? V no load minus V full load. Okay, divided by V no load into 100. Okay, so this is V rated minus V full load, or we can say divide into 100 in terms of percentage. So a machine with low value of SCR, okay, what will have happen is that if it is having a low short circuit ratio, has a lower stability limit, as the maximum power output of the machine is inversely proportional to, sorry, this is no, so voltage regulation. So basically a low value of SCR means what? Means that the synchronous reactance has a larger value. Okay, so if you carefully see, this is V by I. Okay, so the synchronous reactance, if you have a low value of SCR, that would mean your reactance value has a larger value. Okay, so if the reactance value has a larger value, synchronous, see, only this low SCR will happen if the current will increase. So current will increase only if the synchronous reactance is having a larger value. So what happens is a low value of SCR, we can state a low value of SCR means value of SCR means that the synchronous reactance synchronous reactance reactance has a large value, has a large value has a large value. Synchronous reactance has a large value. Synchronous machine with low value of SCR thus have greater changes in C in voltage under fluctuation. So basically, if it has a large value, so that would mean essentially the whenever we are applying the load, the reactive load on the secondary side, so this V full load would be okay. The variation of V full load to V no load would be large. So that would mean synchronous machines with low value of SCR, synchronous synchronous machines with low value of SCR, low value of synchronous machines with low value of SCR thus have a greater changes in voltage, thus have a greater changes in voltage under fluctuation, under load fluctuations under load fluctuations. That is one thing. So the inherent voltage regulation of the machine would be poor. So that means the voltage regulation value, this value would be poor. So poor means if you are getting more voltage regulation 10%, okay, that is considered poor, because voltage regulation should be between 3 to 5%. So we will get more voltage regulation value, because this will be greater, this will be significantly. So this is 220 minus 100, 120, 120 divided by this 220, so you will get around uh, 11 1 by 5, so 50%. That is not desired. Okay, if there is more voltage, see here, I'll give you an example in the next slide. Okay, suppose you have the greater voltage regulation, this is 220. Okay, and you get this as let's suppose 110. Okay, divided by 220. So let's see the voltage regulation at that time. So this will be again 220 minus 110, this would be 110 by 220. So this is 1 by 2, or this is zero point 0.5 into 100. So the percentage, this would be 50%. Is this desired? 50% voltage regulation is desired? No, this is not desired. No, not desired. So this was what I was trying to explain you. In case of a voltage regulation, the voltage regulation should be between 3 to 5%. So if this is 220, uh, this should be around 210. Okay, then divided by 220. So 210 divided by 220, or let's say 200. Okay, 20 divided by 220. So this is 2 11s. So 11 ones are 0.00. So this would be point 11 nines. Okay, 9 99. So around this is around point into 100. This is around 9%. So this is like uh, it should be even lesser than this. It should be around 220 minus around 210 or something like this. So this would be the fluctuation. We'll see the voltage regulation should be around this level. Okay, so now we understood, like, if the voltage regulation is like the inherent voltage regulation of the machine becomes poor in case of this. So we'll write down, if this is the case, the inherent voltage voltage regulation of machine becomes poor. So this is one case. Okay, poor. Okay, this is one case. So then what are the other factors that is affecting the machine? So machines, all the, if you check, if you go to your higher semesters also, so what happens is, as far as the machine is concerned, okay, uh, you will notice the machines are connected, like the generators and all. These are connected in parallel. Means no, there is not a single machine to the system. You have an infinite you have many machines to the system, and we are connecting it to one bus. So this is also termed, so suppose you are connecting one alternator to the already existing grid, so this grid is also termed as infinite bus. So you're connecting, there are so many machines, so these machines have to operate in parallel. So for to operate in parallel, the machines have to be stable. So if you are connecting machines with different frequencies, it will not work. If you are connecting machines with the different ratios and other parameters, because they have to be synced, different phase angles, okay, different polarities, it will not work. So we have to connect the machines in parallel. While when we are connecting while we are connecting while we are connecting, we need to we need to connect machines in parallel and in sync. So in sync means they should have following characteristics. Okay, the machines need to have following characteristics. So the number one characteristics of the machine should be that in they should have same polarity. Okay, same polarity. Okay, this is very essential. Then they should have same phase angle. Okay, phase angle. Okay, the number third thing, the machine should have same sequence. If it's a three phase machine, sequence means what? This is RYB. Okay, so that sequence they have to follow. Okay, they cannot, one machine cannot be in another. There is only two types of sequence. If you will notice, one type of sequence is like this: R, Y, and B. Okay, now this, if you notice the sequence, you have the sequence like this. So this is anti-clockwise. Okay, anti-clockwise. Now if you have to write the sequence clockwise, now if you have to write this R, okay, now the same sequence should be written clockwise. So the clockwise R will remain as it is. Okay, so this will become R, Y, B. So that's what happens in an induction motor or in any machine. Suppose the machine is rotating anti-clockwise. Okay, so this machine is rotating anti-clockwise. Now if you want it to rotate clockwise, you have to interchange any one, either Y, B, or any one sequence you interchange. If it is rotating clockwise, it will start rotating anti-clockwise. So these are the things that machines have to have. So what are the factors that are affecting? So one of the important factors that it will affect is the stability of the machine to run synchronously. So the important factor herein is the stability of the machine. Suppose this is the positive sequence, this is the negative sequence. So there are only two types of sequences, okay, in the machine. Okay, now uh, uh, suppose, yeah, now the fourth one would be the stability. So stability, so how does it affect the stability? Now a machine with low value of SCR has a lower stability limit. Okay, why it has a lower stability limit? Because the maximum power output of the machine, see, maximum power output, see, power is equal to EVX sine delta. Okay, so this is the power that we generate in the synchronous machine. You must have studied the formula also if you have forgotten. Like this is also EVX sine delta. Okay, wherein sine delta is the torque angle. Okay, X is the synchronous reactance. Okay, this is the terminal voltage, this is the excitation voltage. So you must have studied this formula. So please revise it. Okay, stability. A machine with low value of SCR has a lower stability limit. Okay, a machine with low value of SCR, low value of SCR has a lower stability limit. Lower stability limit. So this is one important factor, has a lower stability limit. Okay, and as the why it is so, as the maximum power, the maximum power you will see as as the maximum power of the machine, maximum power output of machine is inversely proportional, inversely proportional to reactance. So here you see from this particular formula the maximum of P is equal to EVX, so this is inversely proportional to it. Now the third point that I wanted to tell is the parallel operation. So parallel operation, this is the third point, that is the parallel operation. Parallel operation. So we essentially saw the conditions for the parallel operation, so same polarity, these things. So how does it affect? So what will happen if a machine has a low value of SCR? So machines with a low value of SCR are difficult to operate in parallel. Okay, machines with low value of SCR are difficult to operate in parallel. So these machines are difficult to operate in parallel. What is the reason for that? Because as usually we know, because they have, because it has because it has a high value of synchronous react, high value of synchronous reactance. Okay, so this high value of synchronous reactance is there as the machines with the this high value of synchronous reactance. So what does it do? It gives a small synchronizing power. So it gives small synchronizing power. So we know the synchronizing power formula. I will write it down one more time so that you understand. So it gives a small synchronizing power. So if we see the synchronizing power, P is equal to EVXS. So if it has large excess value, it's in the denominator. What happens to the power? Power becomes less. So this is the reason it becomes less. So okay, so power. This is responsible for. See, what happens is that this power is responsible. So this power is responsible for keeping machines synchronized. So this is the power that is responsible for keeping the machine synchronized. So this is an essential quantity we have to see. So the parallel operation of machines with high value of XD becomes more difficult if they are interconnected through a transmission line. So what happens is, uh, so another point is that if you will notice the machines, it becomes more difficult to to perform, we can say, to perform parallel operation of machines interconnected via transmission transmission line. So this is okay. This is one concern we have. So why is this so? This is because what happens is, if you notice, the impedance of the line between generator adds directly to the sum of impedance of the machines. Okay, so we have, when we are connecting it, okay, so there, through the transmission line, these are the, if you will see, if in the later chapters you will see there is a generator. Okay, after the generator there would be a transformer. We don't directly give it to the, but this thing, you will have a step up transformer. Okay, step up transformer. So you are connecting, so you have connected a generator, step up transmit, then there's a transmission line. Okay, so similarly it goes. Okay, now now you have another transformer, step down transformer. Okay, step down, then again line. Okay, again line, again some step down, then again here finally you will give to the load. Okay, so what happens is that if it says low, so there is like the transmission line is predominantly inductive in nature, so it has some inductance. Okay, so this inductance plus the generator's inductance adds up. So that is one of the reasons, why this is happening. So what happens exactly is, we can write down. So this happens, this is because we can write, this is because, this is because the impedance impedance of the line, of the line between the between impedance of the line between the line between generator you saw this is the line. Okay, so this is the line, transmission line. This is like this transformer generator. What happens is, generator adds directly to the sum of impedance, to the sum of impedances of the machines. So what it does is that machines, this increases the impedance. Okay, overall impedance will get increased, and it will act to reduce again the synchronizing power. So what happens is that this further increases, okay, excess, that is, it further increases your synchronous reactance, and resulting in decrease of synchronizing power. So this is PS. So on the next slide I'll write. So this further increases, what it further increases synchronous reactance, synchronous reactance, resulting in decreased synchronizing power. So this is what happens exactly. And by this the machine becomes, or the system becomes, more sensitive to torque. And if it is having a low voltage regulation, what happens is the system the system becomes more, we can say, susceptible or sensitive. The system becomes more sensitive to torque and voltage imbalances, uh, to torque and voltage imbalances, or we can say disturbances. If there is some disturbance in the system. So these are the three criteria we saw. So uh, now another thing is that a small value of SCR indicates the smaller value of current under short circuit conditions, owing to what? Owing to large value of synchronous reactance. This is not a problem because the short circuit currents can be limited, and thus the synchronous reactance. So this is another thing, is that the short circuit current which we have to see, like what are the other factors it is affecting. So this is the short circuit ratio. What about the short circuit current? Short circuit current. So what happens to the short circuit current is a small value of SCR. A small value of SCR indicates what happens. A small value of SCR, that is the short circuit ratio, indicates a small value of what? Indicates a smaller value of current under short circuit conditions. Under short circuit conditions. See, this is why this is happening. This is happening owing to the large value of XD. Okay, this is owing to large value of synchronous reactance, that is excess. This is synchronous reactance. So this is all because of this particular synchronous reactance. So this is because of this. So this is not that much a problem. It can be handled easily because this is not that much. This is not a major problem. This is not a major problem because the short circuit currents, because the currents, that is the, because the short circuit currents can be limited. Okay, can be limited, and thus the excess value. Okay, so we can, but the last factor over here is the self excitation. You know, in a synchronous machine, what happens, how it synchronizes it, uh, as you saw about the induction machine, it is a singly fed induction motor. Okay, we don't have a supply on both the sides. But if you see the synchronous machine on the rotor side, okay, and on the stator side, on the stator side we have a DC field excitation. So we have a DC generator around 0 to 250 volts, okay, near to it. So the field winding is also is getting excited in case of a generator, and the motor is also getting the supply, okay, in case of a motor. So we have supply, until less what happens is that when we remove the excitation, we remove the excitation when the rotor locks with the stator. So as the name suggests, it's a synchronous machine. So synchronous machine means it will always be running at a synchronous speed. So here, like machines feeding long transmission lines should not be designed with a small SCR, as this would lead to large voltages on open circuit produced by self excitation owing to large capacitive currents drawn by the transmission line. So we have to check, like machine self excitation means this is the machine, synchronous machine, we are putting it with a transmission line on the other end. Okay, this is the real machine which generates the power that is coming to our home via the transmission line and the transformers and the other gears in between. Finally that is landing to the distribution transformer near our home, then from the distribution transformer through the service means to our home main supply. So this is what happens is that these machines are feeding long transmission lines. Suppose the power is generated something in Karnataka, there is a thermal power plant. Okay, very far away. I am not getting the name. I have visited also that place in Kerala also. So far off locations, exactly the power is getting generated. From there, that power is getting supplied to your home via the transmission line and the other thing. So machines are essentially feeding a long transmission system. So machines feeding long transmission line, machines feeding long transmission 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 lines. Machines feeding long transmission lines should not be designed with a small SCR. Okay, should not be designed with a small SCR. Why they should not be small SCR? What happens? The thing is, because because a machine because a machine with small SCR would lead to lead to large large voltages on open circuit produced by self self excitation owing to owing to large capacitive currents. So capacitive current is due to the leakage. Okay, currents drawn by transmission line. So this thing we have to keep in mind. These are the factors that are affecting essentially the machine. So this is one of these are the factors that are affecting the machine and the short circuit ratio of the machine. So this was about the short circuit ratio of the machine. So what are the other things that we have studied? Okay, so another questions we will encounter. This has come for 8 marks previously in the VTO exam. I'm mostly focusing on the syllabus and the VTO system, whatever they are following, so that you should not have any problem. So you have to be in sync with the VTO system and also in sync with the syllabus, as well as whatever knowledge I have for the competitive sort of examination. There little bit I'm providing. So this what is a short circuit ratio? So essentially we know the SCR of a machine is defined as the ratio of the field current. Okay, the same field current. So we can also write, see, V open circuit, okay, I short circuit. Okay, here we have to keep field winding IF. Okay, and this is field winding IF. So IF, so this is basically the short circuit ratio. If you see V by IS, so this is equal to Z also. Okay, because this is also equal to impedance. Okay, so this is equal to Z also. So this is the in other terms, you can also find the impedance of the machine. So that is one of the, and this is the per unit impedance of the machine. Okay, so what is actually the per unit value? If you are having any confusion with per unit system means you have a actual value of a machine, some actual value, and you take a base, Z base, means per unit is just like a dollar. Okay, dollar means how it is like a dollar. Suppose there are different types of money involved in this world. Okay, so there are different money involved. So in case of see, we have different money. We have rupees. Okay, we have yen, we have taka, we have pound, we have euro, we have so much, and we finally have dollar. So dollar is like a common per unit value. So like we express everything in terms of dollar these days. So $1 is equal to, suppose, now I'm not knowing because I'm not a financial analyst. Suppose $1 is equal to 70 rupees. Okay, so 70 rupees, $1 is equal to this 23 uh, yen, something like that, and $1 is equal to zero point 0.9 pound, something like that. Okay, so what happens is that you can see the dollar is a base value. Okay, base value. So we are trying to express in per unit value. So Z per unit would mean anything, any rupees. So Indian currency is your actual currency divided by your dollar. Dollar is your base value. So here you see Z per unit is equal to Z actual by Z base. Okay. So why do we try to express this in per unit? Now $1, okay, this is the per unit value. Sorry, one per unit is equal to zero point 0.7. Okay, $0.7. So what we do is that we take a base value in the machine. Okay, so we have different type of things available. We have a transformer available there. Okay, it will have different impedance. We have a transmission line, it has a different impedance. So what we try is that we try to get all the impedance in term of one value, so that we express it. Suppose the biggest value of the impedance would be that we consider, and divide it with the actual value of all other terms, so it becomes easy to calculate. Okay, when you will be heading now. Power system is this semester or next semester, Ratika? Ratika,
Sir, sir,
a power system subject is this semester or next semester for you?
this semester we
Hmm?
have power electronics, sir.
Oh no, okay, okay. So next semester only. Okay. Now, this was like I was giving you some brief introduction. Till now, you are not studied per unit, huh? Ratika, have you studied this per unit concept previously?
No,
Okay, okay. No, this is like because in the machines sometimes it will be there, so that's what I wanted to explain you a little bit. So one more question, let's see. Okay, discuss the factors to be considered while selecting suitable number of armature slots in an synchronous machine. So this is another thing is to discuss discuss the factors to be considered to be considered while selecting a suitable number of armature armature slots in a synchronous machine. So what are the factors that you will consider? So the solution to it would be the factors that you will need. Number one is your whether the winding, you have to check whether it's balanced winding or not. So what do you mean by balanced winding? So as the number of armature slots must be in such a number that a balanced winding is obtained. Okay, balanced winding means, okay, use of unbalanced winding may lead to overheating of rotor surface due to space or excessively triple frequency currents flowing in the end due to circulation. So what does basically balanced winding mean? Because you have a three-phase machine, okay, you don't have a single phase machine. So R Y B. So last time we similarly we designed for we if we are designing a 36, like for example in this first slot 1 2 3, okay, 4 5 6, okay, 7 8 9, 8 9. Suppose here we have 9. Again here will be 18. Again here we are having 27. So if we are having 27 slots for a three phase winding, so we can say it's a balanced winding. Now suppose and in every slot, like slot per pole per phase is 3, so minimum number of slots we require is 27. Okay, if we have 3 slots per pole per phase and we have only 24 slots, so this winding is not balanced, it's unbalanced, because in the third slot we don't have all the slots filled. So this is basically balance winding. So the number, and you have also noticed there are certain phenomena, okay, of the harmonics that are getting produced, okay, due to unbalance. So these are the triple harmonics, okay, and this is the harmonic frequencies you have seen 6n plus minus 1. So in case of the induction motor, you saw a phenomena of crawling existing because of the harmonic, seventh harmonic. And seventh harmonic is again a odd harmonic. So similarly, in an induction machine, when you are constructing an induction machine, you should make sure that the windings are balanced. If you are okay, there are so many unbalanced windings. Your two phases are balanced, but the third phase is unbalanced. Although the machine will operate, if you start an induction motor with three phase and remove one single phase, machine will still operate with two phases also with a reduced rating capacity, but it will operate. But what it will do is that it will lead to the overheating due to the unbalance that is produced by the removal of the third phase. So this is something of importance. The number of armature slots must be such as that the number that such to such the I'll write down. So this was the explanation. The number of armature the number of armature slots must be must be in such a number in such a number so that so that balanced winding is obtained. A balanced winding is obtained. So this is one phenomena that is required. The other thing is that use of unbalanced. Now you are using use of unbalanced winding may lead to uh, overheating overheating rotor surface due to space harmonics due to space harmonics excessive triple frequency currents flowing in neutral and due to circulating currents and due to circulating currents in other generators running in parallel. So this is one important phenomena that we require is the balance of winding. Then what are the other factors we require is that the cost. So this as usually uh, the other factor here would be the cost. So how does it affect? See, if you have a smaller number of slot, this would lead to a slight saving of copper because there are a fewer coils to wind and form, insulate, and place into slots and connect. So usually when we were designing, even though we are getting larger number of slots, but what we considered is that if we are getting the optimum design with the lesser number of slots only, we were going for the lesser number only. If you will check in case of induction motor also. So this cost is one important parameter. So I'll write down cost. Uh, small number of a small number of slots leads to say slight saving in copper or whatever material you sometimes you also use aluminum also because copper aluminum or any other metal. Okay, you can say metal because there are fewer coils to wind. There are fewer coils to wind. Okay, and form means forming it. and shape, okay, and insulate and to place into slots and connect. So this is one important factor. Then the other important factor here is you have your hotspot temperatures. Hotspot temperatures. So what exactly is hotspot temperature means? See, when you have a smaller number of slots, it results in bunching of conductors. If the conductors are bunching, so what happens is that it leaves a smaller space for the circulation of air. So if they are placed one after the another, so there is no air gap in between, so it leaves a lesser space for the circulation of air through it. So this gives to a rise of high internal temperature on those spots, resulting into hot spots. And we have to be careful while shooting the selecting the suitable number of armature slots so for the hotspot temperature. So what is hotspot? Basically is a small number of slots. We'll write down a smaller, sorry, a smaller number of slots, a smaller number of slots results in results in bunching, results in bunching of conductors, results in bunching of conductors, leaving smaller leaving smaller space for the circulation of air, for the circulation of air. This gives rise to high into this gives rise to high internal high internal temperature. Now another thing is that the leakage reactance, okay, leakage reactance. So leakage reactance, how does it affect the system? So as far as the leakage reactance is concerned, so what happens is that when the number of slots, if you are taking small, so leakage reactance is going to increase owing to conductors lying near to each other. So that also your leakage reactance is increasing. So your this thing happens is that uh, it also affects the selecting of the number of slots. So you have to see that whether you are bunching the slots, whether you are taking the optimum slot. So this is another parameter. When the number of number of slots is small, so what happens is is small. So you what you do is that leakage reactance is increased. Leakage reactance is increased owing to what? Owing to conductors, owing to conductors lying near to each other, lying near to each other. And this was the fourth point. Now the fifth point would be the tooth ripples. Tooth ripples. So what are these tooth ripples? So the tooth ripples in the field from the consequent pulsation losses in the pole face. Okay, what happens is that so the stator tooth, these are the ripples that ripples formed. See, we have these structures. Okay, these are the tooth. Okay, here the ripples formed in stator tooth. We can say stator tooth result result into pulsation losses consequent one after the another consequent pulsation losses. So when we are designing so this thing, so it results into pulsation losses. So pulsation losses um, in we can say the pulsation losses in pole phase decrease if a large number of if a if a large number of slots are used. So we can see there is a balance between the maximum number of slots we can use and the lesser number of slots. So in some operations, maybe we will look at larger number of slots compared to the lesser, because we have to encounter the pulsation. If for a large machine, we'll see there would be greater pulsation losses compared to a small machine. There is lesser pulsation losses. It can tolerate the pulsation losses, so we will save in copper. Okay, so this is how a design is taken incorporated. Okay, and then so flux density in the iron, this is another factor. Okay, factor number 6, flux density in iron. So can you explain me tomorrow? I want you to explain me this flux density in the iron. How does it affect it? And because already I have taught you this flux density. This is the B average value. So I want the class to start. So tomorrow I have class on next class I have on Tuesday. I want a flip class from you, because I have to conduct. So as far as the flip class is concerned, Monica, you have given flip class. Monica, Monica,
Yes, sir.
you have given flip class.
No, sir.
So Monica BR, huh?
Ah, sir.
Both the Monica, both the there are two Monicas, Monica BR and Monica V. Okay. So and I want from one more fellow is there, Danush Kumar, Danush Kumar, Danush Kumar. Tell to this Danush Kumar also. Okay, Danush Kumar. We will do it on I think Tuesday afternoon or Friday. Tell me. Friday we will do. Friday will give, because you will tell you are not giving a time. So this is Monica BR. You explain me. Okay, output equation. Okay, output equation of synchronous machine. Synchronous machine, and Monica V and Danish Kumar. Monica V, you can explain me the today's only. You explain me, no problem. Discuss the factors to be considered. Okay, where it went. Factors to be considered for selecting suitable armature slots. And Danush Kumar, Danush Kumar, Danush Kumar is there, no? Danush Kumar, tell to Danush Kumar, Ratika, huh? I will mark him absent today. He is not. Danush Kumar, where you are, and you have to explain short circuit ratio. Danush Kumar is not there, huh? Okay, so Manohar has given. Danush Kumar is not listening. Avulva was also given. Durga Rani, Durga Rani, Durga. Okay, Durga Rani. Yeah, you present this, okay, because you have not given this, and you can present this instead of Danush Kumar. Durga Rani. Okay, go for this SCR what I have taught you today, and you can leave the meeting and join the next class. It's already to 12:23. I'm sorry, I did not notice it. I'll stop recording. Okay, you can join the. You already give the attendance.